In this problem, we are presented with a simple spring mass damper system. We just have one mass, one spring, one damper that we are applying this external force F of t to, and we are interested in deriving its transfer function. And then we want to simulate its response to a step input, a 10-unit step input, and we'll do that in MATLAB. And also to verify at least the initial and the final values we get in MATLAB, we're going to apply initial value theorem, final value theorem to our solution. So the first step is we are trying to find what I will call g, the transfer function, where our output is going to be the position x, and the input is going to be that force F. And first I'm going to get this algebraically. I always want to do as much algebra versions of things first and then apply numbers when I have to. Like when I go into MATLAB, since we're not doing anything symbolically in MATLAB, I will have to work with the actual parameter values. We have a mechanical system, so I'm going to start in my first step by drawing the free body diagram of the system. In this case, there is only one object that we need to draw the free body diagram of, and that will be the mass. So on our left-hand side, I'm going to draw all of the forces that are affecting this mass. We are given the coordinate system of x positive down here, and that's what we'll be staying with. I'm not going to rewrite the coordinate system since one was given to us, but there'll be nothing wrong with establishing x positive up, driving everything that way. It's just that our inference at the end would be the opposite of what's positive and what's negative. All right, so on this mass m, we are going to have forces from the spring and the damper to which it is attached. And we saw this before in section 3. For springs and dampers, I'm always going to draw them in tension. And I'm going to derive their values assuming tension. So positive tension, negative compression. Right, so we have a spring coming out, and this is showing its in tension, and the damper is in tension as well. So the actual value of that force we need to think about based on the coordinate system x that we were given here. So x is positive down. So what we want to think about is, will a positive x or a negative x cause the force in the spring, let's say first, to be in tension? Well, the top of the spring is attached to the ceiling, which cannot move. So if x is positive, that is going to stretch the spring, thus putting it into tension. So a k times x is what we want here, a positive k times x in particular. Because again, when x is positive, this quantity will then be positive, and if x is negative, it's going to be compressed, and then the quantity, the product, is going to be negative. And that's what we want to happen. Positive tension, negative compression. Now again, we're assuming, and for the most part we are always assuming, springs are going to obey this linear relationship that the force in the spring is k times x, and that is, unless otherwise said, what we're going to be assuming. Moving on to the damper, same idea here. It's going to be either the top of it is attached to the ceiling and the bottom of it to the mass, so the ceiling part cannot move, so the tension or compression of the damper is completely determined by the velocity x dot of the mass. So again here, will a positive or a negative velocity cause the damper to be in tension? A positive velocity means that the mass is traveling downward, stretching the damper apart, and thus putting it into tension. So this too should be a positive x dot. So a positive b times a positive x dot. When the velocity is downward, it's being put into tension. That agrees with how we drew the arrow. When x dot is negative, the mass is traveling upward, putting the damper into compression and making this quantity negative, which again agrees with the way that we drew this. So in this picture, kx and the arrow is up, bx dot and the arrow is up. And the other force acting on the mass here is going to be the applied force F of t, which I'll just leave as F of t for now. And we don't compensate for gravity. That's already being taken care of by the spring because we are going to be moving from equilibrium. X of t is measured from equilibrium. All right, those are all the forces. It can only move up and down. We are not allowing for it to move left or right or to rotate, so we have a single degree of freedom. The mass can travel up or down along that x-axis. So drawing the inertia, Again, only one degree of freedom, so we draw it in the positive direction of that degree of freedom, and that will be our mx double dot. And that's all there is to that right-hand side. Our free body diagram is now complete. Pretty simple for this one, since we just have that one element that we have to worry about. So now we can derive its equation of motion using Newton's second law. So from our only free body diagram, if we sum forces along that x direction, well, it's going to be the left picture equal to the right picture. In the left picture, I'll start from the top to the bottom. So in the negative x direction, we have k times x. Right? So it's negative because the arrow points along the negative x axis. Same idea for bx dot. That arrow is pointing along the negative x axis, so it's negative in this equation. Same idea we used in statics, in strength of materials, in dynamics. We're following the coordinate system that has been established. Our arrow is positive for f of t. It goes in the positive x direction, so plus f of t. That's everything on the left-hand side. That equals, again, the arrow is along the positive x-axis, so positive mx double dot. We have our equation of motion, which is this ordinary differential equation. It's second order. We have this mx double dot term, the x double dot term in particular here. So we need to get to, in the end, the transfer function. We want x over f. Right now we're in the time domain. The transfer function is going to be in the frequency domain. So I want to take the Laplace transform of both sides here. And I'll take some shortcuts because on the left-hand side I have this sum. Remember, the sum, the Laplace transform of a sum is the same as the sum of the Laplace transforms. So saving a little bit of time, I can say it's negative k times the Laplace transform of x minus b times the Laplace transform of x dot plus the Laplace transform of f of t equals, and now the right-hand side, I can pull that m out because it's constant, Laplace transform of x double dot. I'm going a little bit more longhand than I'll do in future examples just to show where is the transfer function coming from. So I have to do the Laplace transform of all of these time-dependent variables. X is a function of time, as is f. But what we also want to remember is this system started at equilibrium. It's initially at equilibrium. We start the timer, then we apply this force, this f of t. So x of 0 is 0, x dot of 0 is what that means. And that's going to be true anytime we're working with transfer functions, because the transfer function depends on initial conditions all being 0. And we'll see how that makes the Laplace transform also much easier. So resolving these Laplace transforms, negative k, the Laplace transform of x is big X, or x of s, minus b times the Laplace transform of x dot is going to be sx. And then really it's minus this x of 0 when we do it, but remember that our initial conditions are all going to be 0, so this term is going to drop out. It's just 0. Plus Laplace transform of little f of t is just big F of s. So I'll put the of s there just to remind us, but we don't know at this moment what f of t is. Later we're told it's a step function. Here we just treat it as some function of time. So when we do its Laplace transform, it just becomes big F of s. We'll resolve that with more specifics later. Equals m times Laplace transform of x double dot will give us s squared big X. And again, we would have that x of 0 term, we would have that x dot of 0 term also here, and we would have an s in front of one of them, but both of these are 0, so that is going to drop out as well. So at this point, I'll just erase them so it's a less to c because they all dropped out because of initial conditions being 0, being at equilibrium. All right, so the goal is still going to be the same as it has been for going for, if we wanted to solve this, we want to isolate x on one side, and in this case, we want to isolate the input on the other. And it's a good idea. Here it's going to be pretty simple, but when we get multiple degrees of freedom, it gets a little bit trickier. We want to just keep track of what are the inputs and what are the outputs at this step. So f of s is the input, that's our force input, and x of s is our one output. We're going to need as many equations as we have outputs. Now, right now it's not a big deal because we only have one output, we have one equation, we're done. But we're going to see as we get to more complicated situations, we'll have multiple equations of motion, but at the same time, we'll have multiple outputs. So I want my output isolated on one side and the other side to have my input, constants, and s terms, and that is all. All right, so what I'm going to do is move over the x terms to the right-hand side here. And I'll keep the f on the other side. Out of habit, though, I want my x's on the left-hand side, so I will just kind of flip the direction of everything. So I have a plus bsx, and I have a plus kx from moving it over, and now my right-hand side has that f of s term. I can factor out x from the left-hand side, and I'm left with this ms squared plus bs plus k equals, I'll drop the of s right now, and finally I can isolate my x term is going to be my f over ms squared plus bs plus k. And the final step is I actually want the transfer function. So at this point, now I have g, which is generically what I call transfer functions typically, is my output over my input equals 1, since I divide through by f, over ms squared plus bs plus k. So this is algebraically at the moment the transfer function for this simple spring mass damper. And algebraically, this is the transfer function really for every spring mass damper system is always going to look like this. Now, we still want to derive it, make sure we're doing things right, but this is going to come up a lot in this course when we are dealing with these 1 degree of freedom systems, is this 1 over ms squared plus bs plus k. We like to work with simple spring mass damper systems, and what's going to change it is the values on m and b and k. Now I will put in now the numerical values that were given for m and b and k. So we are told here an emsh of 0.1. So this will be 1 over 0.1 s squared plus our b value is 0.4. So plus 0.4 s plus our k value is 6. Now notice here I'm working with all base units, so I'm not including units here. I always want to be working with base units, kilograms, newtons, meters. M, B, and K were already given to us in those base units, so there's nothing to convert at this moment. So I'll leave it here in our base units, so that's 1 over 0.1 s squared plus 0.4 s plus 6 is the numeric version of this transfer function. So this is part 1 answered. We have algebraically the transfer function that takes us from the force input F to the displacement output X. And also we now have it numerically as well. So we've stepped into part 2 a little bit. So now what we want to see is what if we specify what the input is. As a reminder, this transfer function we just derived didn't care about the specifics of the input. It just said, okay, there's some force input into the system on the mass, so this is good for any force system that is being applied to the mass. Now we'll get specific and say in this problem that that force input is going to be a 10 magnitude step force. So 10 Newton step force. And what we want to look at is what happens to x of t starting at time equals 0. So we immediately apply this step function to it. What happens to the displacement of that mass? Well, we're going to do this numerically using the transfer function tool and the step function in MATLAB. But what we can do before we get there and do it numerically is at least we can know what happens at time 0 and as steady state as time goes to infinity using the IVT, the FVT, the initial value theorem, the final value theorem. So we can do more of this by hand before we get to the numeric output from MATLAB. We do have to be a little bit careful though, because I want to know not what happens to g as time goes to 0, time goes to infinity. G is just the transfer function. I care about my output, in this case, x. So I do need to just modify this for a second and say that x equals, I should go back to this form, f over 0.1s squared plus 0.4s plus 6. This is my x of s, and this is what I'm going to be doing the limit of, not g, and that's a very common mistake to make. Because remember, what are we looking for? Let's say initial value theorem first. So let's do IVT. This tells us that x steady state, which is, I could express as the limit as t goes to infinity of x of t, is the same as the limit of s times x as s goes to 0. So I need to see what happens to s times x. Well, I just defined x above. It's that f over 0.1s squared plus 0.4s plus 6. I also have to put in some details here. So I was told that f of t is 10 times the step function, which we can use this u of t notation, or sometimes I will use this h of t for the Heaviside function, or sometimes I might say it's like 10 times 1 of t. So just as a notation note, this u of t, h of t, and 1 of t, I am going to use interchangeably as the unit step function. So just as another reminder, what do these all mean? Well, the unit step function is defined as, it's really a piecewise function. It's 0 for t less than 0, and it's 1 for t greater than or equal to 0. So basically, if the time is negative, it's 0, and it turns on when the time is 0. Now, you might see other definitions for this that are going to say, no, it's actually this. It's 0 for time less than 0 or equal to 0, and it's only 1 when time is positive. And also, you might see one like this, probably less frequently. When time is exactly equal to 0, it's equal to 1/2. I'm going to go with that original definition I'm using. Functionally, it really doesn't make a difference because it's that moment in time is the only difference. Are we including 0 or not? It's really not going to make that much of a difference in our analysis. So that's how we're going to use this step function. Now, if I take the Laplace transform of f of t, that is, well, I've been calling it f of s. But now I can be more specific because I know what f of t is. I want the Laplace transform of 10 times u of t. Well, that is equal to 10 times the Laplace transform of u of t or h of t, depending on which table we're using. So that is going to be 10 over s, which is f, or f of s. So now that I know specifically what my f of t is at this point, I can substitute that in up here because it's 10 over s. So this is going to be 10 over 0.1s cubed plus 0.4s squared plus 6s. So it's a little bit cramped there, but again, I'm putting in for big F 10 over s. So that's why the denominator was raised by 1, its power was raised by 1, and I have a 10. All right, so now back to initial value theorem. A little bit of a side investigation there, but now I want to take the limit as s goes to 0 of s times x. Well, here's s. X I just defined above, so that's 0.1s cubed plus 0.4s squared plus 6s. Now it does turn out in this case that I actually get right back to where I started in a sense, because that s on top now cancels one of the s's on the bottom. So indeed, it does look exactly like, well, except for the 10, but the denominator looks just like what we had for g. But I am not taking the limit of g. It just turned out that because I had a step input for f, and I'm multiplying by s to use initial value theorem, that the denominator looks the same. But that is by chance of what my input function is. It is not universally true. All right, so now I can apply s is 0 because my denominator is not going to be 0 here. So this is going to be 10 over 6. which is 5 over 3. And that will be roughly, so we have a decimal equivalent here, it's going to be about 1.6 repeating. As a correction, this is final value theorem I just did, not the initial value theorem. I'm looking at what happens as time goes to infinity of x of t. So the final value will be this 1.6, or 5/3. Now I can do the initial value theorem. So I want to know what happens initially. So what is the limit as t goes to 0 of x of t? That is the same as the limit as s goes to infinity of s times x. All right, so I already defined what that was. So this is going to be 10 over 0.1s squared plus 0.4s plus 6. Right? And then initial value then, because my denominator is of a higher degree, then I know that this is going to be 0 as s goes to infinity. Right, so final value, it should go eventually to 5/3, and initially it should be 0. Now, this was all done analytically. Now we're going to test it numerically in MATLAB to see if we agree at least time is 0 and steady state, and MATLAB is going to tell us what is happening in between. So as a reminder, what we're going to be doing in MATLAB is using the transfer function and simulating putting in a step function of 10 units into it. So we will be creating the transfer function g, this 1 over ms squared plus bs plus k, when we look at this MATLAB step. Now we're in the MATLAB. MATLAB we cannot do, or I'm not using symbolics in MATLAB, so I am going to define the m, the k, and the b right away, again in their base units. So I'm just going to run up to that point. M, b, and k are entered. Now what's a little different than what we just did analytically is I have to create the transfer function. Right? So this is my g that I'm creating, this x over f on line 8. So if I run this, notice what I'm doing. I'm using this tf function that tells it, make me a transfer function, where the numerator in descending powers of s is just 1, which would be the s to the 0 or 1 power, because that is, the numerator is just 1 times s to the 0. And then the denominator, again, with the coefficients in front of descending powers of s. In this case, I have my s squared, my s, and my s to the 0 or 1 term are being multiplied by m, by b, and by k, respectively. And if I run line 8 and print it, we can just make sure it did it the way we wanted it to. So yes, this is exactly what we had for that transfer function that we wrote down by hand. So replacing in the parameters for m and b and k, we have the 1 on top, 0.1s squared plus 0.4s plus k. So our transfer function has been entered correctly. Now, to simulate what happens to x, we're keeping it as a transfer function, and I'm using the step on the transfer function. So it's a little bit different than what we did for the initial value theorem, final value theorem here. I'm here using the transfer function itself, and MATLAB knows what to do with it, because what the step tells it is, okay, here's the transfer function. F, the denominator of this, or the input into this, is a step function. Show me what the output looks like. So here I am directly using the transfer function. By hand, I did have to multiply through by the denominator, by that input, in order to know what happens to x. But the outputs now are going to show me the same thing. So I want a step input of, here I'm specifying 10 units, and I want it applied to my transfer function g. So that's what line 10 is going to do. And if I just use step like I have on line 10, it's going to make this plot for us automatically. Another way to use this step, if I go into the help briefly, is I can actually save on the left-hand side the output. And if we notice how we use it here, you can put in the output y and the time t and save that into vectors, and then you can do the plot yourself, which sometimes we want to do. If I just put this step and then what the system is, in this case 10 times g, it's going to make the plot for me. So just be aware of that, that I would say not always do we want the default plot it makes. we might want to, and often do want to, customize what it looks like. So again, by default, this is the plot that it made for us. And actually, let me modify it just a little bit so it's easier to look at. So I'll run this whole cell and remake my plot so things are a little bit bigger. Okay, so this is the plot it makes for the output. Remember that x was positive down the way it was defined in the original problem. And let's see what happens, I guess, first at time is 0. Our initial value theorem predicted that our initial time, at time 0, our initial position is 0, and that is also true or corroborated by this numerical solution. And we said that at steady state, which it kind of decided when steady state was achieved. It doesn't quite look like it's flat, but if we look at the amplitude by 3 seconds or so, we have an amplitude of 1.67, so that is very close to that 5/3 that final value theorem said was going to be the steady state value. Now I can do a little bit of modification to step if I really wanted to. By default, it's going to try to figure out where the steady state value is, but I can also specify a time span to use. So I'll just use a linspace here. It originally went to 3 seconds. Let me take it out to 5 seconds. And I'll just use 1,000 steps in between. And now, this optional argument is what times to use in my simulation. So again, I'm going to start at 0 and go to 5 now with 1,000 steps. So I should get more flat. Here we see from 3 seconds to 5 seconds now. It's definitely flatter. We've definitely gone to steady state. And once again, we have this agreement here that the amplitude goes to 5/3 as final value theorem predicted. Now, what initial value theorem, final value theorem did not predict or tell us anything about is what happened in between. So let's see. We hit it with that step function at time is 0, so it's going to go down the positive x direction. It's going to have a displacement with a maximum of about 2.4 meters below the equilibrium point. That's pretty far. These numbers are made up just for this example, but we see that it peaks 2.4 meters below the equilibrium point. But then it is going to start to come back. Its x value decreases, it gets closer to the equilibrium point, and it's going to come back up and only be 1.36 meters from the equilibrium. Now notice here, x is strictly positive. In this case, it never goes above the equilibrium point under these circumstances. Then it goes further away, but only up to that smaller amplitude, about 1.8. It comes closer, goes further away, and then it settles in because energy is being lost as it moves. It's being dissipated through that viscous damper, and eventually it settles to its steady state value, that 5/3. Now, once we get to unit 2, we are going to be able to analytically figure out where the peaks are occurring and what their values are, how quickly it's getting to steady state, and all of that will be possible in the analysis unit. For right now, we're just going to let MATLAB do the solution for us so that we can visualize what's happening if we want to, but we're not going to yet be able to analytically predict what is happening between the initial time 0 and our steady state. As a recap of what we did, we had this 1 degree of freedom system, this simple spring mass damper, and we wanted to first get its transfer function. We wanted to do the modeling step. So in this mechanical system, I drew a free body diagram of, in this case, just the one element that could move or that had inertia. So it was a single free body diagram of all the forces acting on it on the left and its inertia on the right. We used the free body diagram to derive its equation of motion in the time domain. It's a single equation of motion because we have only, again, this single degree of freedom. I want to go from the time domain into the frequency domain, so I took the Laplace transform of both sides. X is a function of time, as is f, so it is affected by the Laplace transform, but my constants m, b, k are not, so they can come outside of these Laplace transforms. I then do the Laplace transforms, noting that in this case I started at equilibrium, so my initial conditions were all 0, and that's why after the Laplace transform, we have this pretty simple line in the frequency domain because those initial conditions all dropped out. Now I want to isolate my output x, in this case, on one side and put everything else on the other side, including my one input, f. So I rearranged it to have all of my x's on one side, and then I'm going to let the other side have everything else. I can isolate the x, I divide through, and I get that it's equal to f over this ms squared plus bs plus k. Now, I am not going to do an inverse Laplace transform. I want a transfer function. So this is where we deviate a little bit from what we did in section 3. Not doing the inverse, I want my transfer function, my output over my input. So I rearrange this, I divide through by f to get x over f, which is my transfer function. And I have it all algebraically. So this satisfies part 1. This is that modeling step, which is getting my transfer function. Now I can put in my numerical parameters here for m and b and k at this point. And now I can use final value theorem, initial value theorem to try to see what happens to x at time is 0 and as x goes to steady state. So final value theorem told me at steady state that x should have a value of 5/3, and initially it should have a value of 0. I went into MATLAB and I verified the initial value theorem, final value theorem using the transfer function in MATLAB as well as the step function, and numerically MATLAB told me what happened in between time 0 and the steady state.